Hello and welcome to our discussion of density. As part of this astronomy lab, we're going to look at the mass and volume of planets and then convert mass and volume into density. Of course, mass and volume are pretty big values for on the planetary scale, so we're going to pay attention to exponents in this example pretty closely. Okay? So let's think about what density is. Okay, and let's think about weight. What weight is? Okay, weight is a function of gravity. It's not the same as mass. Mass of something is sort of a measurement of an object's inertia. Okay, so it's a sort of perfect measurement. Whereas weight is, or it's intrinsic to the object. Whereas weight is a function of gravity. Okay, so it's proportional to something. A measurement that is proportional to its mass, but it's also a function of, let's say, the planet that you're on, right? So Mercury is a smaller planet than Earth. It has less gravity. Same with with Mars. But if you went to Jupiter, you might find that there's a significantly larger gravitational attraction between you and the planet, and so you're going to have a much higher weight. Okay? Density is a measurement of mass divided by volume. So we're going to learn how to mess around a little bit with mass and a little bit with volume, and then we're going to end up calculating density and making a plot of these values with respect to the solar system. So you're confronted with this page here, where again you have to list the planets in order from their distance from the sun. So you might want to go ahead and do that right now. And so you get Mercury, and then Venus, Earth, Mars, and so on, all the way down to Neptune. For each of these planets, we're going to calculate their mass, and then we're going to also calculate their volume. So let's do an example where we deal with the mass first. Okay. So depending on how you want to do this, sometimes I move exponents around, sometimes I don't. Okay? And I'll show you how I shift them around, but my introductory lecture on exponents will be useful in this case. So let's do this for Mercury. All right, so Mercury has a value of 0.055. Okay, that's its mass relative to Earth. We've normalized everything else to Earth, so it means Earth has a mass of 1. Okay, so Mercury has less mass than Earth. The actual mass in kilograms of Earth is 5.98 times 10 to the 24th. So if we want to figure out or back calculate the actual mass of Mercury, that's going to be this value, 0.055 times the mass of Earth, 5.98 times 10 to the 24th. Okay, no problem. So I'm going to write this in a specific way. 5.5 times 10 to the minus 2. Okay, 5.5 times 10 to the minus 2 is the same as 0.055. Okay. That's why I was showing you how you mess around with exponents. Okay, and we're going to do that times, so I'll use an asterisk here just so we don't get confused with our exponent values. 5.98 times 10 to the 24th. Okay, well, what did I say? First you do the decimal values, and you end up with, in this case, 33.19. You could round that to 33.2, okay, times 10. Okay, now for multiplication we add, right? So now we're adding 24 plus minus 2, which actually gives us 22. Now, most of the time we want to move that decimal into this position so that we have one significant figure before the decimal, and so we're going to do 3.3. And we can round it to 2 if you want. 3.32 times 10, okay, to the 23rd. Move it to the left. We're going to add an exponent to our value. We're still going to get the same value, and that's going to be kilograms. Okay, so that is our mass. Now, we also want to calculate the volume for Mercury, so I'm going to go ahead and write the mass in here. Okay, mass is going to be 3.32 times 10 to the 23rd kilograms. Okay. Next step is to do the volume. So let me go ahead and erase the work I've already done for mercury, and we'll treat the volume in a similar way. We'll go 5.6, right? 0.56 is what's written here, times 10 to the minus 2, okay, times 1.08 times 10 to the 12th, okay, is equal to 6.05 times 10 to the 10 kilometers cubed. Right? So this turns out to be the volume of mercury. Where did this value, 1.08 times 10 to the 12th, come from? Well, we started out with the volume of Earth. Volume of Earth, is 1. We've normalized it to be 1. Mercury is a smaller volume, so 0.056 times 1.08 times 10 to the 12th gives us 6.05 times 10 to the 10 kilometers cubed. So now that we have mass, we can divide it by volume, and we can end up calculating the density of the planet. So if you jump down one table, you end up on the density chart here, the density table, and again you have the planets. I'm going to move this thing a little bit. So there you have the planets. You have to list them in order. And you'll notice that in this area where it says show work, you're going to want to do that work and adjust the values a little bit. So we want to do it in grams per cubic centimeter. Okay, that's different than the units you've calculated it in the previous table. Let's jump up for a second. Previous table, we're using cubic kilometers, okay, not cubic centimeters, and we're using kilograms. So we need to make some conversions and change our values a little bit when we put them in to this particular table to show our work. Okay, so let me go ahead and erase some of this. So what's this going to look like? Okay, it's going to look something like this. I'm going to come down to the bottom. Okay, we're going to do the density calculation here for mercury. So we start out with 3.29 times 10 to the 23rd. Okay. Now we need to convert that from kilograms to grams, so we need to multiply it times 1,000. Okay. And so that ends up becoming, or adding 3 zeros to our value, so times 1,000. Here we end up with a value of 3.29 times 10 to 26, so a pretty big number. But this is going to convert it from kilograms to grams. Okay, so now we got the units we want. On the right-hand side, we've got quite a big number here, something that might not make a lot of sense to you. We have 1 cubic kilometer is equal to 1 times 10 to the 15th cubic centimeters. Okay? This has to do with the fact that we have to multiply some big numbers by and cube them to get the correct number of centimeters in 1 cubic kilometer. And so we start out with 6.05 times 10 to the 10th. Sorry, getting ahead of myself. 10 to the 10th. Okay, we're going to multiply that by 1 times 10 to the 15, okay, which is going to give us a value of 6.05 times 10 to the 25th. Okay, we go ahead and do the mathematics on this, right? It's going to be 3.029 times 10 to the 26th divided by 6.05 times 10 to the 25th. So a big number divided by a small number, even though the integers here, or the decimal values don't suggest that. The exponents make it this way. We divide 3.29. Okay, 3.29 by 6.025. Okay, we end up with 0.54 times 10 to the 1, right? We want to move this decimal because we want it to be in grams per centimeter cubed. We want to move this decimal so it's 5.4 times 10. Sorry, it's actually 5.4 period, not 5.4 times 10. So it's 5.4 grams per centimeter cubed, right? So this is the answer we want, okay? Two significant figures with no exponents in the equation, right? So up here, when you show your work, it's going to be 3.29 times 10 to the 26 grams divided by 6.05 times 10 to the 25th centimeters cubed, okay, is equal to 0.54 times 10 to the 1 grams per cubic centimeter, and I simplified that down here to 5.4. Okay, so 5.4 is where you want to end up. We're going to make a chart using that. Okay, so if I flip down to the chart, once you've gone ahead and calculated all those densities, we can then go back to where we've calculated the diameter of the planet, which is here on this y-axis, and the density of the planet, which is here on the x-axis. So I just calculated 5.4. So that's right about here on the bottom right-hand side of this chart. Okay, we back up one. Okay, that's our density. What's the diameter of Mercury? Mass, volume. We got to go back to our first page here. The diameter of Mercury is 6,372. Okay. Go forward. Density is 5.4. I'll put that in this table. Okay, now we're at a 6.2, okay, or 6.3, okay, diameter, and that's in thousands of kilometers. So we want to simplify it a little bit. 6,375. We want to simplify it, and we want to divide it by 1,000 and make it small. Okay, so that means this becomes 6.3. Why are we going to do that? So we're going to plot it on this chart here that goes up to 160. It doesn't go up to 6,000. So by dividing it by 1,000, we get a smaller number. So now I've got the density on the bottom right, and I also have, if I go to the mass, which sits right in here at 6.3. I'm sorry, the diameter, which is a 6.3. Mercury plots right there, okay, on my density versus diameter chart. So you're going to plot the rest of the planets. You're going to fill in this table, okay, with all your densities. You're going to go back to the first part of the exercise where you measured the diameters. You're going to divide those diameters. So the Earth, for instance, would be 12,000. It becomes 12, right, which also plots down here on the bottom part of the diagram right here. Okay, and then the density of Earth, I'll let you calculate that. It's already actually calculated for you, more or less. So anyway, that concludes sort of how we deal with density and mass and volume.